My name is Kevin Kwon, and this is Physics Lab 3, Black Hole and Orbits. The purpose of the lab for part 1 was to estimate the mass of the black hole by analyzing the motion of a star orbiting the black hole. For part 2 was finding an initial velocity for the spaceship to get it moving in an orbit around both the planet and the moon without crashing into either one of them. The model was provided in the glow script, and the fundamental physics principles used here are Newton's second law and universal law of gravitation. The system in part 1 was the black hole and the star, and in part 2 was planet, moon, and spaceship. There weren't any surroundings. The findings are shown here. Newton's second law states that the rate of change in momentum is equal to the vectorial sum of forces on the body. The formula is F net equals the change in momentum over change in time, and using that we can find the velocity update and the position update formula. The net force has two components, parallel and the perpendicular component. The parallel component is parallel to the direction of motion and tells us about the change in speed on an object. The perpendicular component is perpendicular to the direction of the motion and tells us about change in direction of an object. Universal law of gravitation states that every object in the universe attracts every other object in the universe. The formula is force of gravity is equal to g times mass 1 times mass 2 over r squared times negative r hat. The gravitational force follows Newton's third law of equal and opposite force. This means that the force that objects exert on each other is equal in magnitude and opposite in direction. These were the initial conditions updated for part 1 for the seed, star, the mass of the star, and delta t. This was the code for part 1 where the momentum was calculated using mass times velocity, delta v and delta p was calculated using final minus initial, and F net was set to delta p over delta t. And for dp dt parallel was also found using the magnitude of p final minus magnitude of p initial over delta t. And from that we can find the F net perpendicular, which is equal to dp dt minus dp dt parallel. And the mass of the black hole is updated in the formula here. This is a short video showing the program running. So for calculation of the mass of the black hole, we can, from the universal gravitation formula, if we isolate m2 as the mass of the black hole, then we can get the formula shown as shown. And by using the data provided in the loop from GlowScript and averaging the masses of the black hole, we get that the masses of the black hole is estimated to be 9.66 times 10 to the 33 power kilograms. Possible sources of error. Because the orbit is in elliptical motion, the time it takes to get around the orbit for the points further away takes more time. Because of that, more data points could have been from the further away points, which means averaging those points further away could mean the mass of the black hole was estimated higher than actual. Also, rounding error could have happened. What does it mean? The net force and the rate of change of momentum is equal. The value of the parallel component is equal to the parallel component of the range of change of momentum. The value of the perpendicular component is also equal to the perpendicular component of rate of change of momentum. But the key difference is the net force always points towards the black hole, but the rate of change of momentum depends on the star's velocity. These were the initial conditions for part 2 provided in the sample code. And in the code, I updated all the formula using the universal gravitation formula. These were the results for the part 2 that I came up with. The motion is pretty consistent using the initial velocity negative 19,500 meters per second and 25,000 meters per second in the x and y direction respectively. Through trial and error of different initial velocity combinations, I figured out that making a 8 orbit was not possible. So possible sources of error, there could have been rounding errors, and also the assumption of point mass instead of mass distributed over the planet, moon, and the spaceship could have caused errors. There was also incorrect guessing of the velocity because there was no mathematical formula to find it, but rather was a trial and error. So if I wanted to predict the motion of the entire system with black hole, star, planet, and the moon, then the computational model should have the net force affecting every object in the system. In other words, all objects in the system should be exerting a gravitational force on each other, and none of them would stay in the same initial spot unless one object is massively larger than others. For example, the black hole would exert gravitational force on the star, planet, and the moon, and all of those would also exert an equal and opposite force on the black hole.